This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon. We continue from yesterday. Before I start, though, don't forget to upload your workshop reports. I think it's end of due this week, right? It's in LMS, workshop 2, and then we will start workshop 3 next week. I haven't posted it yet, but I'll post it probably tomorrow. the workshop 3 manual, which will be on neural networks. And that's what we are going to also start with next week. I have already posted the slides there in LMS. Let's see if we can finish the supervised learning today. If not, that's not a big problem. We can finish it early next week and then continue with the neural. And let's see. So I was talking about the kernel methods, and we have discussed. I've motivated the kernels through one perspective, and then haven't gone in deep into its usefulness and how we use the kernels. They can be used in multiple places. And the idea was doing an implicit transformation. And it turns out all we need is the dot product of the transforms of the dot product of the futures x, of the data points in the future space. So if we call phi of x the transformation of data point x to the future space phi of x, defined by phi of x, then any dot product in the data space xn xm, for example, dot product in the future space, then it will be phi xn phi xm, and that is given by the kernel function. So the kernel function gives us the dot product in the future space or in the transformed space, and as we will see, this is quite powerful and useful. And then you can have different types of nonlinear, linear and nonlinear kernel functions. So you can that also gives us a lot of freedom to choose something that works for our problem, right? And then we talked about this question 4, some simple dual representation in linear regression. This kind of illustrates how you can use kernels in a regularized sum of squares, and then we have gone over an explicit solution that gives us, the solution y of x in terms of the kernel matrix and the function based on the data points, right? So that means we can choose different kernels, we get a different result. Of course, when you choose different models, you get different results, but Here, for this linear regression problem, we get an explicit solution. So I think I haven't done question 5. So let's continue with 5 and 6. Go a little bit deeper into the kernel method stuff. Better understand how these kernels work, and then we will go to support vector machines, where they are heavily used. One of the major use cases of kernels. So question 5 is actually quite easy, and what does it say? Show that an excellent choice of kernel. Okay, let me make it a bit bigger, right? So it says show that an excellent choice of kernel for learning a function f of x. So that's a regression problem, right? Is given by kxx prime. So this is the kernel function defined with respect to 2 data points, right? Now it's defined in a very special way, right? This is the tricky part of the question. So it says if you want to learn f of x, use this kernel k of k equals f of x and f of x prime. Just multiply them. And how do we show this is an excellent choice? That linear learning machine based on this kernel will always find a solution proportional to the f of x. So what is a linear learning machine based on this kernel? Essentially, it is this. So we have the y maybe another color. So we have the y y of x, and then over all the data points n equals 1 to n, some alpha n, parameter alpha n, and k x xn. So this is the kernel with respect to x and xn. So if we have such a linear learning machine, it's linear in this kernel, as we can see. Will it always find a solution proportional to f of x? I don't know. We can substitute because we are given the k here, right? So we have the k here. The kernel is given. And if we write it down, we have then n equals 1 to n, alpha n, and then f of x n, and then times f of x, right? So I just substituted. Notice that xn is part of our data set. Xn belongs to our data set. That's right. And once we learn the machine, then we will know alpha n as well. So that means this whole first part will be a constant then, once we learn it. Once we train, equals c constant after training. Right? Therefore, it is we have y of x indeed some proportional to f of x. And then, yeah, we are happy about that. All right, what's the catch with this question? There is a paradox in the question. You can detect it in the formulation of the question. We are trying to learn f of x, and the kernel is f of x and x1 and f of x2, right? What's the paradox?
Basically knowing the model to guess the model.
Yes, exactly, right? We don't know f of x. How can we use the kernel with f of x? If we knew f of x, we wouldn't need to learn it. So exactly, you know, and as you say, so the model, the kernel is using the function we are trying to learn. That doesn't make sense. This is the function we are trying to learn. So that's why it is nice exercise, but doesn't mean much in practice. Okay, so that's just again spending a little bit time with the kernel machines, and then this is actually a better question in the sense that it kind of proves what we have said. So I kind of said in the slides that, you know, we have a linear model, then the the parameters of the linear model will have have this form plus the perpendicular ones, which are orthogonal to the space spanned by the data set, and then they will not play a role. Therefore, they will not be. We will not care about them. So can we show that? So that's the that's an example of that shows it. So let's look at a parametric model by the parameter vector w, together with the data set input values x1 to xn, and we have a nonlinear feature mapping phi of x. Suppose the dependence on the error function, we have a regularized error. We have an f of the values, and then this is a monotonically increasing function. We use it as a regularization term. So this is a quite general form. We want to minimize the error, and then we can write the w as we have said in terms of the future vectors plus some additional component, where this additional component is orthogonal to these individual future vectors defined by the data points. So then the w that minimizes jw takes the form of linear combination of the basis functions, and this will be 0. That's what it says. So that was already in the slides. So we can go through its derivation in a bit more detail now. Right? So we first write it in the most general case. So we write it as a linear combination of the future vectors over all the data points. There's a lot of redundancy here, right? Some of the alpha n's will be 0 if we have tons of data points, plus this additional term that is orthogonal to the future space. So this can be written as the inside this future space and orthogonal, and the inside one is a linear combination. So, since we have this orthogonality, then it immediately follows that these two are the dot product of the orthogonal, and inside is 0, as we have said also in the slides. So this is straight. If you multiply this one with this, obviously these zeros will cancel out, so you get a 0. Right? Until now, it's okay, right? So we have a kind of a linear space, and then the null space. The orthogonal ones are in the null space of that linear space, and the linear space is spanned by the future vectors, by the data points and futures of the data points, phi of x's. Yep. So I don't know how would we visualize it. Maybe this is the for example phi of x1, and this would be the phi of x2. Then the orthogonal one would be then the W orthogonal. So you see this is orthogonal to both of them, right? It's outside the data space. So if the data future space is this plane, right, then the W orthogonal, not one, this is in the doesn't belong to that space plane. Huh? That's a kind of a visualization. Now, you see, if we take these two together, and we have this, we can actually write now our cost error function that we try to minimize simply in this form. So it is written as W times phi. Every W can be written as a sum, right? And plus also the G. But the cross terms will be 0, so then they all cancel out. So this one cancels out when it multiplies. This one cancels out. The cross terms also cancel out. So we end up with this, the W parallels that are inside that space, and then G, this one and this one. Now, G is monotonically increasing, and this is a quadratic term, right, in the orthogonal ones components, and this is non-zero. This is always greater than or equal to 0, right? And because it's monotonic, while we are trying to minimize, then the minimum will be achieved at W orthogonal equals 0, because G is increasing in its component, and then this is positive addition. So of course it will be minimum when you make it 0. You cannot make it less than 0 because it's quadratic. So then you see that the JW is written all in terms of these inside the linear combination components, and none of the orthogonal ones appear anymore as we expected. So then we will have W that is as a linear combination of in the future space, and spanned by the data futures, and that's what we were saying in the slides as well, and that's what the question was asking. So it's a kind of a nice clean derivation of the whole thing. Is this clear? It requires some basic linear algebra background knowledge in terms of null spaces and so on. But once you remember those things, then it is quite straightforward. And the intuition was, so what is the intuition? Intuition is very simple. My parameters are a function of my data, or futures of my data, which is very reasonable, right? My parameters come from the data and nothing else. Any component of the W's that don't belong to the space defined by the data, they will be 0. So in that sense, it is also a very good intuitive explanation beyond the algebra part. All right? Yeah? Okay. Now the main dish, kind of, like we have done a little bit of, we played with kernels a little bit. Let's go to the support vector machines and let's do some classification. Right? That's one of the important things to do in supervised learning. And as I was saying, there was a time support vector machines were the main game in the town in 90s until the whole deep learning thing. That was the main thing. Support vector machines was the main dish, main popular method. And as we will see, it has also a lot of nice mathematical characteristics. All right, here's the thinking. So we talk about separating. First, I will focus separating two classes, right? So, and then if you have more classes, you can actually separate in a step-by-step, like a tree structure. So for now, let's focus on two-class case, just like we did in the logistic regression initially. And I have the blue dots and the green dots, and I want to draw the line to separate them, right? That's the job of classification. That's the whole thing. And now I'm not going to do any probability theory here. It's all about drawing this red line, and this red line could be linear or it could be nonlinear, right? It could be a line, it could be a curve in two-dimensional space. So let's start with a line. If I can separate them with a nice line, then why should I draw a complicated curve? So that's it. Then that would be a simple linear discriminant function. So I can define y of x, which is this red line, in a general I'm sorry. In the general case, then it will be a hyperplane, not a line, of course. It would be a line, plane, then a hyperplane, right? Two-dimension, in three dimensions, the data points, I need a plane to separate them. And in the n dimensions, it would be a hyperplane. You cannot visualize anymore. So that would be defined, the hyperplane is defined by this. So there is a normal vector, and then there's the x is the point, and then omega 0 is the bias threshold. And this is the weight vector. So that's the function. And then an input vector is assigned to class C1, maybe the blue dots. Then if y of x is positive, and to class C2 if y of x is negative. And if y of x is 0, then you are exactly on the separating surface, right? That's the indeterminate case. Right, so y of x is 0 is what we see here. And this is a really nice figure that exactly says this. So, as I said, it's a d minus 1 dimensional hyperplane in the d dimensional input space. D is 2, then it's 1. D is 3, then it's 2, and so on. Okay, so I've also included this slide because it puts a lot of geometry here, and then analytical geometry. So I'm hoping this will help you, when you review, it will help you demystify some of the things. So you see the region 2 and region 1, we again have a linear hyperplane separating the space into two parts. And this is the W, and this is any x. By chance, x is now in region 1, but it could have been here as well. I can write x, I can actually make a projection of x to the plane, right? And then I can write it as two components. One component is this from origin to the plane, and the second component is from plane to the x. So I can write it as a vector sum, right? X is a vector. A point in space, therefore written as a vector. It can be written as a sum of these dotted vectors. Now, this is red is our y of x separating hyperplane, dividing the space into two parts. Y of x equals 0. Y equals 0 is that means I'm on it. Greater than 0, I'm here. Less than 0, I'm here. And we can also write this as this, right? So we can actually, when it is 0, y of x equals 0, I can take omega to the left-hand side, becomes minus omega 0, and then I can divide both of them to a fixed quantity, which is norm of omega. So then I can actually, I have this equation, right? So I can obtain that. And as I mentioned, x is there's the sum of two vectors. One is the orthogonal vector plus the distance to the separating hyperplane, and that's the distance as a scalar times the direction. Of course, in order to make it a vector, actually all I need is the direction of w. Direction of w is that would be unit vector, right? When I divide w to its norm, then I get a unit vector. So r times the unit vector in the direction of the w will give me this vector, and then the other vector is this one. This r is kind of important, the scalar, that is the distance of x to the hyperplane. And one can show, I am not showing it here, that it is y of x divided by this norm of omega, norm of w, I'm sorry. So that's the distance definition. So I should put maybe a link. You can check. There are multiple places where you can derive this, how you find that distance as a scalar, right? Okay, so that's kind of a cheat sheet for you, geometric cheat sheet. Now we come to the main idea. So we have a set of data points, and then each data points have these labels, in this case t's, and then it is convenient, actually, it turns out, to make these t's -1 and 1. There's a reason for, you can also make them 0, 1, or 1, 2, whatever. You can do it whatever you want, but -1 and 1 is quite convenient if it's a binary. And if we consider this binary classifier, actually, if we have the hyperplane, that is our classifier. If y of x is greater than 0 and less than 0, right? Then we have the future vector. Actually, we don't have to even do it in x, right? We can now do it in the future vector. We can do a phi of x. So that would be that would make it nonlinear, not necessarily linear. Phi of x could be x, or phi of x could be something else. Plus b is the bias. So that's the omega 0 in the previous thing. So, and as I said, once we have this, positive means labeled +1, negative means labeled -1. So we have two classes. And note that this +-1 thing is useful because of this. If I use now then tn times y of xn, if it's -1, then this is also -1. Minus is plus. If it's plus is plus. So this is always positive. And that's something I'm going to use in the math. It makes the math go easier, which is useful, right, as I said. So the title of the slide is Maximum Margin Classifier. So I want to have a separating hyperplane, but I have a lot of choices, right? So let me go back to this. So I can actually draw a lot of options here, right, to separate these clouds of points. I can draw it like this, I can draw it like this, I can draw in different angles. That would be still valid. But what is the best one out of those? The idea, people said, why don't I maximize the margin and find the separating hyperplane that maximizes the margin. So we need to find the w and b after making the modeling choice phi, such that the margin, what is the margin? Defined as the perpendicular distance between decision boundary hyperplane and the closest of the data points. And if I maximize the margin, then I'll be happier. So I kind of put it just smack in the middle. And that kind of makes me, why? Because it will make me do less errors if there's noise, for example. If these data points move a little bit, if I'm just in the middle of them, then that will not affect me. So, for example, if this point is here and this point is here, this will be the closest point. That determines the margin. Or in this ideal, kind of a nice ideal case, you see these points are here and this point is here. The filled dots and the circles, and then by chance both of them are the same distance, and I choose the middle of their distance, right, the closest ones. So that's the whole maximum margin classification business. It makes, so that's what I was saying. In most of the time, your observations of the data can be noisy. So if this shakes a little bit and this shakes a little bit, if you put it to the middle, you are not affected. So it kind of gives you automatic robustness. It's a kind of a good thing, right? So that's the one motivation for it. Now, let's, of course, this, I want to put it to the middle of the closest points. I need to say this mathematically, and when I say this mathematically, it turns out this is an optimization problem. And then we are happy that we learned optimization problem. You will see very convoluted expositions in books, including Bishop's, because many machine learning books cannot assume that the students know optimization. So they kind of have had to introduce them, to introduce the learner, the support vector machines. Many of the machine learning books have to teach the readers the optimization. So I've already done that. That's why I'm kind of feeling a bit more comfortable, and I hope you too. So when we pose it as an optimization problem, we will be in safe waters. So distance of the closest point to the boundary and the margin, as we said, is this. So we have put it before, right? So this y of x and divided by w, that's the distance of an x close to the x to the hyperplane. That's the scalar distance. And depending on plus and minus, we have a slight problem. But when we multiply with the label, that problem goes away. So this is always positive. And therefore, this denominator is actually Tn times y of x and divided by this. This is the margin itself, right? Then what does maximizing the margin mean? We want to find the w and b. That's our model. Given phi, or phi could be x, then it's a simpler case, special case. We want to maximize 1 over w for the which is the margin. We will actually have a question to explain this, for the points that are closest, minimum for these, right? So that's the, this is actually a problematic optimization problem. So you have a max and min inside each other. So fortunately, this nasty optimization can be simplified. So it turns out, you know, y of x is written as w times phi of x plus b, right? So and then all I need is y of x is positive or negative, remember? So if I multiply w with a constant and b with the same constant, let's say k times w and k times b, then this will not change anything in terms of, if y is positive, it will be still positive. If it will be negative, it will be still negative. So I can actually scale w and b without any problem. So that means if we can scale down w and b, then we can actually scale them in such a way that for the closest point, this equation equals 1. And for all others, then this equation will be greater than or equal to 1. Because I'm making the closest point 1, everything else will be greater than 1. So I'm actually, yeah, here, I'm making this to be the 1. The closest point, that quantity, for this point, I make that 1, and then everyone else will be farther away. So then the problem becomes, if I have this, so I try to then minimize, because this was in the denominator, if I put it, maximize this, 1 over means minimizing itself. So I can minimize 1 half omega w squared, such that now I have the constraint for all data points, all of them are greater than or equal to 1. One of them will be the closest one, of course. So if you look at this, this is actually a quadratic programming problem. And it's a convex optimization. So that's really nice, right? So it's a QP. So because the objective is quadratic in this, and then there is the constraints are well defined. So here constraints are convex. Of course, it's actually phi of xn are fixed, right? So they are in linear. This is actually, these constraints are linear in our decision variables. They are linear in our decision. So these are linear inequalities, and the objective is quadratic. So it's a quadratic program. Now we introduce the Lagrange multipliers, and write the Lagrangian. So in this case, let's call the Lagrange multipliers not lambda, but A. I'm following Bishop's notation. So that's useful because if you go and read the book, you don't have to translate. Then one for each data point, because we have noticed that we have as many constraints as the data points. Each data point brings one additional constraint. They are because for all n, and we have n data points. So therefore, we will have n constraints means n Lagrange multipliers an, and these are inequalities, so an will be positive, non-zero. So they are not equality constraints. There are no equality constraints in this problem. So exactly capital N constraints. The Lagrangian is this, and then I just take the derivatives with respect to the decision variables w and b. W is a vector, so you can take the with respect to individual components. And once you take the derivative, it's pretty straightforward that you can see b disappears, and then we get these equations. And then if you substitute this in, what we get is, it's actually, I'm leaving it as an exercise, but if you substitute back in both of these, you get the dual function. And the dual will be done in terms of the ANs, and then this term. And because there's an interesting thing, the phi's will multiply, and then because the kernel phi transpose phi, we can define it as a kernel function, well-defined kernel function if phi is well-defined, a good choice. Then we have an equation where we have a kernel. And as I said, Lagrange multipliers are greater than equal to 0 from Kuhn-Tucker conditions, KKTs. And then this additional constraint comes from the, when we took the derivative with respect to B. All right, so this is, most of the time, the SVM is solved through its dual. Because as you can see, there were n constraints in the primal version. In the dual, you have only positivity of the Lagrange multipliers, and then there's this one more additional constraint. So it's much easier problem. It's an objective function and a Lagrangian and a single constraint. So the dual is easier to solve. That's why, and it also has this nice kernel. So remember the kernel trick that we talked about? The kernel, one of the kernel tricks, the nice property of the kernel, I don't need to even know phi's. I can actually define the kernel directly and solve the support vector machine. All I need is the dot product in the future space. And kernel function provides me that. So if you want to solve it, then we substitute this in, and this was the solution. Once we find the A's and B, and then we can write the A's back. So we get the W we have here, plus B. And from the KKTs of the dual problem, that is this initial part. B, I haven't solved it yet. I will come to that. But before coming to the point, there KKTs of the dual problem are these, as we have discussed. And this is kind of important, the complementary slackness, right? This one tells me something special. For every data point, right, this n subscript n is the data points, either an is 0, because this has to be 0, right? Either this is 0 or this parenthesis is 0. Parenthesis is 0 means Tn Yn equals 1, right? So either I am, the constraint is either not active. Remember, Lagrange multiplier 0 means constraint is not active, or I have this Tn Yxn equals 1, but that means those points are closest to the boundary, as we discussed. So those are the points that are closest to the boundary. So the points with positive Lagrange multipliers are called the support vectors, because they essentially define our hyperplane. Not the faraway ones, the closest one. Because it makes sense. I am defining the boundary using the closest points. And they define the boundary. So when you solve the optimization problem, those points, actually, these circled ones, have positive Lagrange multipliers. and they play the role. All other data points, their Lagrange multipliers are 0, and they don't play a role in defining the y, right? So because when you write it down in terms of Lagrange multipliers, y of x is over all the data points, but multiplied by the ANs. Those data points that do not have a positive Lagrange multiplier, they will be just not considered, and that will make our life a bit easier. Then if we just put this into the picture, then we can also find b. Once we know a and then this additional property and y, we can also get the bias term. So that's, once I have also the a and the b, t n are known, k is known, xn's are known, x is my input, so it gives me y, and then whenever I give a new input, all I need is to check whether y is positive or negative, and then that tells me which class my sample, new sample x belongs to. All right? So that's the whole story actually, and again you can multiply by a constant and it will still work. That's still kind of an extra freedom. And the support vectors are those that have the positive Lagrange multipliers from the dual problem. And that's why it's called support vector machine. So the name comes from there. Okay. So without further ado, maybe let's do these two questions, and then this will give us a little bit more insight. You know, that was a lot of words. Let's go back to some derivation, and maybe this will make things a bit clearer through the examples. So this is actually an interesting, really nice question. It says that show that irrespective of the dimensionality of the data space, a data set consisting of just 2 data points, one from each class, you know, green and blue, is sufficient to determine the location of the maximum margin hyperplane. So yeah, 2 points will be enough to draw a separating hyperplane. Regardless of the dimension of the space, you can divide it into 2 pieces. So can we show this mathematically? And then let's do the math, as I say, to get a kind of an insight. So let's say there are 2 points belonging to the 2 classes. X1 has a label T1 equals +1, and then X2 has a label T2 equals -1. So then when we write them down, W transpose X1, so this is a linear version, so therefore not phi of x, but just x. So therefore W transpose X1b will be +1. These are the closest points, right? So because they are the closest points, we have decided to make their magnitude to 1 while scaling. So, and then Wx2 plus b equals -1. The other one is the -1. And when you multiply with the labels, you get again both of them will be positive. So maybe an explanation is good here. So we scale W and B to make these to make it +1 and -1 for these closest points. We use that freedom to make these +1 and -1. If you ask where does this +1, -1 comes from, maybe it's just plus epsilon and minus epsilon. I multiply with 1 over epsilon, make it +1, -1. All right? So that's good. So then we can actually then solve the write the Lagrangian of the primal. Write Lagrangian of the QP primal formulation. What would that be? You can go back to the slides. What do we have? We have argmin with respect to these 2 things of the 1/2. We put the 1/2 for convenience. Norm square plus now lambda for 1 And now these are equality constraints because there are no other points. And specific x1 point put here, b minus 1. And then the other one will be then maybe mu or n eta. Let me follow the same notation. x2 plus b, in this case plus 1, right? So that would be my Lagrange multiplier, and then I write it this way. Then take the, I'm sorry. So that would be my L, right? LWB. So then we take the partial derivative of L with respect to W and equals 0, and partial with respect to B equals 0. And if we take these, actually this will give me W, and then the what do I have? Lambda x1 and eta x2. So I get, and then that's, yeah, then that would be giving me 0. So I have this W plus lambda x1 plus x2 equals 0. And then the other one gives me, with respect to B, yeah, that will give me then lambda plus eta equals 0, right? So from here we immediately have them like as minus of each other, and then we substitute it in. We get then W is lambda. We can write it in terms of lambda x1 minus x2. Okay. And then we can we substitute it and get the B out of this. So that was the first part. What was I trying to do? I was actually I got the W out of this, so that's one result. I think maybe I should highlight this, and then now using this with maybe the star. Let's put a star here. We combine these two, would give me then, if I sum them up, for example, it would give me zero here. If I sum them up, 0 here, 2b here. So 2b will be minus W x1 plus x2. And then combine this. Actually, this is directly from star, adding two equations, give me this, and then combine these two. Once you combine them and play with a little bit with this, you get the B equals minus lambda over 2 x1 transpose x minus x transpose 2 x2. So I've got the W and B. Notice both of them are in terms of lambda, right? So I can now write y of x equals W transpose x plus B, right? That's my basically decision boundary. In this case, linear, but this will be done. Note that this is y of x has a lambda, positive as a lambda, so it can be scaled, and it would still be valid. So we don't have enough equations to get rid of the lambda, but we don't need it either. So it's we can scale and still get the same result. More importantly, even with 2 points, I can find a separating hyperplane, in the original data space, without any future vectors, without any future transformation. I haven't used the kernels here; just stayed in the. I've done a linear discriminant function, linear separating hyperplane. So that's directly obtained from the definition. The next question is a bit more cumbersome, but I think it's also worth making and going through. So let me go through that as well. So show that the value of the margin for the maximum hyperplane is given by this, and then an are the Lagrange multipliers, as we defined in the slide. So there's nothing new here. So we want to find the value of the margin. And it turns out the value of the margin, maximum margin for the maximum margin hyperplane is given by 1 over rho square, and that's the sum of the eigenvalues, an. That is kind of an interesting result. An are positive as well, so this margin cannot be negative. All right, so that is interesting, but we can actually derive that and find it. First of all, we remember that the margin is defined as Tn Yn over this, the margin value. I multiply with Tn to make it always positive. Otherwise, Yn can give negative value. But when I multiply Tn with Yn, actually Yn or y of xn to be more precise, then that is how you define the margin. Right? That's the margin's definition. Sometimes we say definition with a column and equality. So that's the margin's definition. So first of all, for the maximum margin hyperplane, we know also that Tn and then yxn equals 1, right? Plus b, y of xn equals 1. So therefore, the margin rho equals, because this is 1, it's 1 over w. So rho equals margin. But then, therefore, we have 1 over rho square is w square. So that's good, but that's not the end of the story. So now, for the maximum margin solution, we need to go and write the Lagrange multiplier. Interestingly, for maximum margin solution, if we plug it into the Lagrange multiplier, we have WB and the WB. We have 1/2 W squared. I'm just writing it from the slide. And then what was it? It was sum over n. It was an. When I plugged it in, the y of xn, again from the slides, and then we had the Tn, and then y of xn minus 1. And remember that this is all overall the data points, right? So remember, for all the data points, either an is 0 from KKT conditions, or this is 0, right? So either this is 0, or I should put a big or here. Either this is 0 or that is 0 from complementary slackness in KKT. From KKT complementary slackness, right? Condition. So therefore, this side is 0. Sorry. Why is this not working? Yeah. So this is all 0 for all data points. Either those data points are support vectors and their an is positive, but when they are support vectors, then Tn yxn is 1, therefore the parenthesis is 0, or they are not support vectors, their Lagrange multipliers are 0. So that removes this. So, but if we think about this with the dual, remember we were writing again from the slides, this W can be written in terms of the Lagrange multipliers as this. In the most general case, I can even put to phi of xn. I don't need to assume some linearity here. And I write then the dual. The dual will be then sum of an, again from the slides, minus 1/2. And that would be then an Tn. If you go back to the slides, you can write that double sum over n there's a double sum in the dual that writes like this, phi of xn, and then you can bring as m, am, tm, phi of xm. So this double sum, if I write it, reorganize it this way, then remember this was the definition of W, so this would be then W, and this would be W, and we have a dot product here. So I end up with then, together, we have 1/2 the square equals, and there is no duality gap, because this is QP, right? If you solve the dual, you get the exact same solution. That is important. There's no duality gap. So this value equals then sum of an minus 1/2. Then if it's the dot product, that is the same as square. And then I got the 1/2 plus 1/2. I get the W square, but that is same as 1 over this, which is the which is what we have been looking for, right? So this we have been looking for this. So this is then equal to an, right? So this is the result we have been looking for. Let me delete this. So we end up with this result. Again, this question I like it because it kind of allows you to dive into the equations of the primal and dual, and you know we establish also this relationship of the margin, how much margin I end up with the support vector machine. So what have we done? We have taken the definition of the margin and the properties of from the margin and the maximum margin Harper plane properties. We have written the margin definition, but we don't know the W's. So we have written the primal formulation, which from the complementary slackness, this right-hand side is 0. We have also looked at the dual, and then because we have this W definition, also we know this already known. Once we plug it in, we see that this can be written as this way. Then primal and dual, they have the same. No duality gap, therefore we equate and then write it to obtain what we have. Interesting relationship, 1 over margin square is the sum of the Lagrange multipliers, or you can write it, the margin itself then will be what? Like we can write it also, we do it more meaningfully. It would be then 1 over square root of sum of an, right? It will be, yeah, it will be like that. 1 square, it will be equals, yeah, it will be then square root of the sum of the Lagrange multipliers. So that will be then my margin. Of course, maximum margin that I am maximizing through the optimization function. So the whole optimization function is the job of the optimization quadratic program is to find the separating hyperplane that maximizes the margin, and it also on the way finds all these support vectors that define that separating hyperplane. Before I finish, just one last word maybe is again, I want to come back to this slide before I leave you. So what is the, I'm going to continue it next week for sure with a few more slides. What if the data set is not linearly separable? So we can use the kernel trick and define a nonlinear boundary. So as you have seen now with the support vector machine, I can define a phi of x, or I don't even need to define a phi of x. I only need a kernel function. And the kernel function takes my data points and throws them to a kernel future space defined by this phi of x. And I don't even need to know this phi of x. There's a very interesting case that I will cover. So therefore, if your data looks like this, actual data is 2-dimensional, you map it to 3-dimensional, make it like this, and then you have a nicely separable situation, right? Or this is just intuition, right? You can have a very complicated data, two classes that are inside each other, like the two moons. then you throw them to a higher dimensional space through the kernel function. The funny thing is you don't even know what that transformation is. All you need is the kernel function that tells you the dot products in that future space. And if you have the right kernel function, then you can solve the problem. So the question you should ask before we close is, how do I know which kernel function to use? And the answer is,